So this topic is about why some nuclei undergo fission reaction and some fusion reaction. So what is the main factor? What is the deciding factor here? So we can see a graph that is representing binding energy per nucleon versus its mass number. So what is binding energy per nucleus? So we know in the nucleus there are protons which are of positive charges, so they repel each other. But due to strong nuclear force that is provided by the binding mass defect or binding energy, the nucleons that are proton and neutrons, they stay together in the nucleus. Suppose in a system, in a nucleus, we have four nucleons, and in a system we have here n for nucleus, okay, the number of like constituents per part of the nucleus, and we have, for example, 8 nucleons, and in both cases I am providing, for example, 40 electrovolts here and here. So in this case, each nucleus will have 4 electrovolt, and here 5 5 electrovolt. So if you want to separate a nucleon from the nucleus, you need to break this binding energy. You need to break their internal bonds. So that means in this case, you have to fight against 10 electrovolt, and here you have to fight against 5 electrovolt. So definitely, fighting against the 5 electrovolt is easier for you. So stability of the nucleus depends on binding energy per nucleon, not only binding energy, but binding energy per nucleon. So in this figure, we can see that binding energy per nucleus is maxed here, that is iron for 56. So we can divide the graph into two segments, suppose like this. So we have these two regions here and here. Okay, now in any reaction, the goal of reaction is to reach more stable state, and the stability of the nucleus depends on binding energy per nucleon. So if you take uranium, for example, uranium can be more stable if if its nucleus could move to this segment, right? Because in its left segment, the binding energy per nucleon is increasing. And if you take lithium, for example, it will move to more stable situation if its nucleus move towards right. So how they can achieve more stable positions? For for uranium, if you break uranium, so uranium takes part in fission, right? So in fission, what happens? You take uranium 238 and you break it with a neutron. So we take 235 here. So it will create uh, barium and krypton. So barium is probably 56 and it is 36. And then you will have 3 neutron and some energy. Now here, so the uranium, this position is here, and for barium and krypton, you'll get position somewhere like here and here. So you see, these level have more binding energy per nucleon than that of uranium. That means after reacting, their binding energy per nuclear increased. That means they are in a more stable position than it was in uranium. That means by fission reaction, uranium moves to a better stable position. So that is why all the materials at the right of this graph, at the right at this region, takes part in fission reaction. Okay, now if we talk about fusion reaction, we know in fusion reaction two atoms combine together to move to create a heavier nucleus. So suppose we take two hydrogens make helium, right? So for hydrogen, we have here binding energy per nucleon. But if we add two hydrogen, their binding energy per nucleon rises here. That is much stable situation. So the the nucleus that are in this region only takes part in fusion reaction, because by adding two nucleus they can create another nucleus that is more stable, that has more binding energy per nucleon. So if you take uranium, can uranium undergo fusion reaction? It is not supposed to, because if you add two uranium atoms and make another heavier atom, that will create something that has very low binding energy per nucleon, and that is not something natural, because every reaction has the goal to reach a more stable position. So the atoms in this region go through fission reaction, and the atom in this region go through fusion reaction. So that is the condition.